We are given some kinetic data on this theoretical reaction to A going to B. Specifically, we're at specific time intervals, we're told what the concentration of A is. The first task is to determine the average rate of disappearance of A between 0 seconds and 10 seconds. Okay, we'll remember that our delta is always going to be final minus initial. Rates of reaction are to be given as positive values. Since we're dealing with a reactant, we're going to have a negative sign here. In our first time interval, 0 to 10 seconds, here is our change in concentration. So we can pull these numbers directly off of the table. So this is negative 0.625 minus 1.00 molar solution, and our change in time is 10.0 minus 0.0 seconds. Numerically, this is equal to 0.0375, and our units are molals per second, or we can write moles per liter per second. Our second time interval is from 10 to 20 seconds, and we can again read our values directly off the table. .360 molar minus 0.625 molar, and our time frame is 20 minus 10. Numerically, this comes out to be 0.0265 moles per liter per second. Okay, we note here that, as expected, as time proceeds, our reaction rate is going to decrease. We are next asked to estimate the instantaneous rate of disappearance of A at 15 seconds. For this part of the problem, to save time, I stole this cartoon out of the instructor's manual. It plots the data here. For the instantaneous rate at 15 seconds, we go up to the curve at 15 seconds and draw a normal line to the curve at that point. The slope of the line is going to be our instantaneous rate. So picking 2 points on the line, the run is from 10 to 20 seconds, and the rise is from about 0.58 down to maybe 0.35 molar. We can put those values in and determine that the slope is a negative 0.023 moles per liter per second. Accordingly, our estimate for the instantaneous rate of the disappearance of A is going to be the absolute value, the positive value of our slope. Finally, we're asked to consider the rate of reaction with respect to B. And we're going to be looking at two different rates between 0 and 10 seconds, the average rate, and the instantaneous rate at 15 seconds. Here are the relevant rates with respect to A. Now let's bring in the reaction stoichiometry. We know that for every 2 moles of A that is consumed, we produce only 1 mole of B. So the rate of appearance of B is going to be half of each of these rates. And we can crunch out these numbers. 0.0188 moles per liter per second, and in the second case 0.0120 moles per liter per second.